we thought that this was quite fitting, that SSP is held in Montreal in Canada this year. This is only the third SSP that's been hosted in Canada, and we thought that it was quite important to address a topic that was of topical interest to Canada. So for many of you who are international students, international from abroad who aren't familiar with the Canadian environment, Canada's Arctic makes up over 40% of our landmass. So it's a very important ecosystem. It's also essential to our national identity and also of international importance. In fact, it's growing in terms of importance because of climate change issues. It's important for navigation, vessel tracking, and environmental monitoring, as you'll hear from our panelists today. So how this panel event is going to be structured is we're going to have our 4 panelists who are seated over here, and we're going to have them come up and give some short presentations. I'm going to introduce a more full biography of each speaker in between, and at the end we'll have sufficient time for open Q&A. So just to give you an idea of the backgrounds of our speakers today, and I'll give more detailed introductions later. We have 4 panelists. The first is Mr. Guy Hubé. Mr. Guy Hubé is a remote sensing expert from the Canadian Space Agency, from CSA. Second, we have Vern Sinroy, who is an ISU faculty member, as well as working at the Canada Centre of Remote Sensing. He is also the chief scientist of the RADARSAT Constellation mission. Third, we have Professor Ellsworth Ledru, who is from the Department of Geography and Environmental Management at the University of Waterloo. And he is also the head of the Polar Data Catalog, and I'll give more of a thorough introduction later on again. And last but not least is Professor Lyle White. He is a professor at McGill University. He is also the Canada Research Chair in Environmental Microbiology and chair of the CSA Astrobiology DWG. So he's an astrobiologist. I also wanted to add on that this panel event ties in very well academically as well to the SSP 14 program. It's going to tie into some of our core lectures on digital image processing, as well as astrobiology, possibly some policy and law economics type of lectures as well. This is also quite obviously themed under space applications, which is why I'm moderating the event today. I wanted to add that the Space Applications Department actually visited Quebec City, the CCGS Munson, which is a research icebreaker, on Monday, and actually viewed many of this Arctic research and scientific equipment firsthand. So just to tie this into the SSP 14 academic program as well. So I'd just like to ask for you to give a round of applause to our panelists for participating today. I'd like to introduce Guy Hubé. We're going to switch laptops here. And while they're doing that, I'll just give you a bit more background about Guy Hubé. He is a remote sensing expert from CSA. He's been working in the Earth observation applications and utilizations projects and programs since 2005. And he's also been involved in numerous international programs as well. He was trained at the Centre d'Application et Recherche en Télédétection, which is CARTEL, at Université de Sherbrooke. He has a master's degree in remote sensing, specialized in hydrology, and has a bachelor's degree in physical geography. So please welcome Guy Hubé.
Thank you, Sunyin. I'd like to thank also David Kendall for the invitation, and good evening, everyone. So this is it. My name is Guy Hubé. I'm a project manager from the Canadian Space Agency. I'm part of the Earth Observation Application and Utilization Division. The presentation is a review of some of the Canadian success and accomplishments since the last few years in the application of Earth observation data in the coastal, ocean, and Arctic sectors. It also highlights our CSA EO application program contribution and support for the monitoring of changes in the north. So over the past decades, we have witnessed an ever-increasing number of demands in the Arctic region, its coastal zone and resources. At the same time, scientific research and development efforts have been advanced to gain better knowledge and improve monitoring capabilities with respect to changing land and marine environments, ecosystem and human activities. While traditional fishing and marine transportation continue to be prime importance, they are now joined by other uses such as offshore, non-renewable and renewable energy, tourism, recreation, aquaculture, manufacturing and construction, and such thematic as security and defense, as well as public research. There are presently a lot of activities related to the monitoring and understanding of the of changes in the Arctic at the national and international level. This slide highlights a few of our recent reports related to the Arctic region. If you are interested in that subject, I invite you to consult these reports. Some are related to foreign policies, action we need to take to plan for investments. Some other are related to climate change and their impacts, how we can adapt, etc. What is interesting in these reports is that a lot of the source of information is based on information and knowledge is from space and mainly Earth observation, even if it's not written in the reports, but we can deduct that. Canada's economy remains closely tied to the Arctic land, coastal zone, and ocean. As an example, industries linked to the ocean employ about 315,000 and contribute more than 26 billion a year to the nation wealth. When combined with 100 billion trade industry that is predominantly reliant on shipping, ocean and the Arctic activities have an enormous impact on the Canadian economy at large. The increase of activities in the north on the land, coastal, and ocean is raising also security and sovereignty challenges. So our need for tools to map, monitor, and predict short and long-term environmental and man-made changes has never been greater. So how can Earth observation technology help? So among other sources of information, high quality and up-to-date geospatial data and environmental knowledge is needed to plan for environmentally and economically sound growth and to develop more sustainable practices and to protect Canada's northern lands and coastal region. Space-based Earth observation technology and know-how contribute unique data sets and critical information at synoptic as well as detailed, spatial, and temporal scales. Different satellite sensor systems can provide timely, repeatable, and wide area coverage to survey and monitor the Arctic land and marine environments. So science and technology is crucial to build a strong economy that provides high living standard. We know that as technology matures, they become more about benefits, less about features, more about design and applications, and less about technologies itself. Developing Earth observation-based information, product, and services with respect to the Arctic will help governments to increase socioeconomic benefits. So Canada is among the world leaders in Earth observation satellite technology application and utilization. Since 2000, the Canadian Space Agency and its Earth observation application and utilization division have managed 3 main EO-specific programs with well over 250 projects to date. CSA provided support to the Canadian government departments, provincial governments, industry, and university with regards to EO and northern-related activities. Environment Canada, by example, fisheries and oceans, the Department of National Defence have made significant investment to operationalize Earth observation opportunities with regard to the Arctic oceans and coastal areas. So the next slide are really the core of my presentation. It's example of Earth observation application and solution related to the monitoring and understanding of changes in the Arctic. They involve CSA, but also other partners from the federal government and provincial, as well as the private sector and academia. So as a first example, the Canadian Space Agency has enabled the development of the world's first operational satellite-based coastal oil discharge monitoring service called iStop. In November 2006, Canada began to operationally monitor marine coastal areas for oil pollution with satellite SAR. The implementation of this program by the Canadian Ice Service followed the highly successful ISTOP project supported by the Canadian Space Agency. ISTOP is now a national satellite surveillance program for oil detection integrated with Transport Canada and D&D program. This is just an example of an ISTOP product where we can see the presence of a ship and an oil slick with RADARSAT 2. The oil slick is in black here. CSA is also active in the coastal pre-spill domain in the Arctic. The eSpace project, developed in collaboration with Environment Canada Emergency Division, aimed to develop and demonstrate the use of Earth observation data for emergency preparedness, response, and habitat conservation on Canada's northern coast. The goal is to identify shoreline characteristics like habitats and resources at risk in the Arctic coastal zone. Through the CSAEO application programs, we have supported Environment Canada for sea ice mapping activities with RADARSAT 2 and other data such as ASAR. CSA has a long years of cooperation with Environment Canada. Since the mid-1990, we have been working with EC for the provision of RADARSAT data for operational sea ice monitoring, but also for oil pollution, ship routing, and search and rescue operation. This is just an example of an Environment Canada. It's an example of a recent ice product from the CIS. It just highlights the ice roughness in the Cornwallis Island area, and this is in the Arctic. You have the map at the bottom. This is another product from RADARSAT 2. It's a lake ice product in the Slave Lake in Northwest Territory. It highlights the very thick ice versus open water. The imagery was taken by RADARSAT 2 on June 5 and 6. This is another product from Environment Canada. It highlights the unusual presence of ice in Lake Superior. That was in May 1st. And it also highlights some ship and ship track through ice. You can see in white the ship passage. This is just an example of one of the projects we supported with a Canadian company called Infotech. It's a system that they have developed for the navigation through ice. So it's an integrated RADARSAT 1 and 2 data. So it helps the navigators to navigate through ice. This is the Lambert Glacier velocity map. This is not in Arctic, but it's in Antarctica. But I thought that example was a good thing. So by using RADARSAT imagery obtained during the 2000 Antarctic mapping mission, ice velocity vectors were obtained over the Lambert Glacier. Most of the ice shelf has velocities between 400 and 800 meters per year, with a slight slowing in the middle section. And as the glacier extends across the ice shelf, velocity increase up to 1,000 to 1,200 meters per year as the ice sheet spread out. I think Ellsworth will talk more about that. It's part of his polar data catalog. This is an animation from. It's just to show the collaboration between different space agencies. This is the C-28 giant iceberg that was in 2010. So at the bottom, you have an animation made by the European Space Agency. It was made from February 10 to March 4 with ASAR imagery. ASAR was a sensor part of NVSAT. And following these dates, from March 2 to 13, 2010, CSA and we have developed this animation with RADARSAT 2. So it's just to show the continuity and the collaboration between space agencies to monitor some ice changes in polar region. This is a project. This is a product, a river ice product. It's part of a short program we have. It's called RIPS, for Rapid Information Product and Services. We have 4 Canadian companies on standby, and this is for disaster management applications. So we have worked with the government of Northwest Territory here in order to prepare for possible flood. And so as the river is melting during the spring, there could be some ice jam. So with RADARSAT 2, it's possible to classify the ice in the river. So here on the product in blue, you have some open water, and in pink you have some ice jam information. So I guess it's part of the decision making. So coastal water management is another area of activity and support for CSA. Our EO application program have been supporting the development of coastal and ocean water related products directly linked with Government of Canada mandates. So groundwater, freshwater, surface water, and ice products have been developed with RADARSAT 1 and 2. Water quality products have been developed in our Great Lakes, St. Lawrence River, along the Pacific, Atlantic, and Arctic coastal zone. This is just an example of an algae bloom detection with MIRIS. It was also sensor part of NVSAT along the coast of Vancouver. And this is an example of an Arctic bloom in the Barents Sea. It's near just off the coast of Norway, seen by Modis Aqua. So going back in Canada, CSA have supported the development of the Department of Fisheries and Ocean. It's called a web color platform, and this is actually available on the web. And this information is critical sometimes for fisheries activities. So as the water color is linked to phytoplankton, you can predict where the fish goes. So climate and weather are 2 other areas of importance when we speak of the Arctic sector. CSA have been supporting projects focusing on governmental, operational mandate and user needs. Different groups inside the Canadian departments, such as Natural Resource Canada, Environment Canada, have been monitoring climate change and ecosystem impacts, the reduction of ice in the Arctic, and the opening of the Northwest Passage, the monitoring of atmospheric changes, mapping the biomass carbon stock, monitoring and trying to understand Canada glacier and ice cap melting. We have also supported the development of EO projects related to the Canadian International Greenhouse Gas Reporting Requirements. This is also another web platform. It's for ocean wind and waves. It's derived from RADARSAT 2. So Mentor foster the operational use of wind field data in marine and other weather forecasting in Canada and the US. This is an example of Hurricane Gustav tracking with NVSAT and MIRIS, and also with RADARSAT 2. Just highlighting here that ABB Bowman from Quebec City has developed the software and algorithms to allow the selection of and the generation of the MIRIS instrument. And I'm also showing this slide because we know that since the last few years there's a continuation of the path of the hurricanes, but multiple hurricanes are going east, and as we saw this week with the Hurricane Archer, it go up north, and it has hit some northern provinces. But anyway, I guess it's just an highlights that we can track the hurricanes with satellite imagery. So this is a project we have developed with Parks Canada, and it's in the Arctic. It's in Naini National Park. So now Parks Canada is now using satellite imagery to improve its knowledge about ecosystem changes and to facilitate the delineation and new park extensions. Just another project here we made with Parks Canada. It's Silmilik National Park. So again, Parks Canada can use satellite imagery in order to monitor glacier ecosystem in ice field, but also wildlife areas such as seabird colonies. Soil moisture is usually related to the agricultural sector, so more on the south. So this product is a product from some colleagues from Agriculture Canada. They are developing soil moisture from RADARSAT 2 and also from the SMOS sensor. But I thought that that product was interesting because it highlights also some permafrost melting and soil moisture in the Arctic. So I guess in the future this kind of information will be of critical importance. This is a subsidence product made by our colleagues from NRCan. It highlights some terrain movement along a village in Nunavut. So with RADARSAT 2 we can highlight, we can track these soil movements. I guess Vern will talk about that in this presentation. And when we speak about soil movements and subsidence and with multiple images we can detect some changes. So and it has an impact sometimes on these changes have sometimes an impact on the infrastructure. So it's critical to monitor. Here we have it's the Yellowknife area, and the line there is the Yellowknife Airport. So we can see in yellow and orange that there's some subsidence. So it's information for the decision makers. So if the place where the plane land moves, you know that it can be problematic. Yeah, so when we speak of the Arctic and land and ocean, we speak also about the mining industry. I thought that slide was interesting. It's a project we did with MDA. So on the right here, you have it's an open pit mine, and in like the letter A, where is the red, it highlights a lot of ground motion and subsidence. So it's a problematic area. So so when we speak of mine, we speak of safety, but also a lot of economic activity. So there's a lot of people working there. So the project, what's interesting, that slide, that the project was from September 2008 until March 2010. So, and Rio Tinto, which is an international mining company, was part of the project. So the information was given to them. They took the precaution to close a part of the mine because they knew some parts were problematic. So, and in 2013, just to correlate the information we had from the Earth observation data, you can see the letter A, there was a slide. So, so I guess the information we now have with Earth observation is kind of is related to ground truth, and it's critical. And the mine is still open, even if there was a slide, because they can operate the rest of the mine. This is just another example of changes we can monitor in the Arctic. It's a vegetation classification with RADARSAT 2. It's in the Peace Athabasca Delta region. This is just one slide highlighting also another parameters of the land surface, which is wetlands. So on this slide you can see farmlands, wetland area, open water, and some clear cuts. Forest fires is another area of activities. We have been working with Natural Resources Canada. As mainly everybody know, on the optical side we can see some dust and smoke clouds and plumes, and also with thermal imagery we can see some hotspot. But with multiple sensor, not only RADARSAT 2 but also optical versus radar, you can have you can add multiple parameters to some fire model, like soil moisture, biomass, fuel biomass, vegetation type, temperatures. And now NRCan have a system called the Canadian Wildland Fire Information System. It's available on the web, and so it's a recent, I think it's in July 6th. So it's ongoing. So you can consult this website if you want more information about wildfire applications. And this is the last slide, just to highlight that when we talk about change, there's also human activities in the Arctic, and with RADARSAT and with radar and optical imagery, we can track ships and ports and infrastructure. So I guess this is it. I'm not going to talk about RCM because I'm going to scoop Vern, but thank you for your attention.
Thank you, Yi, for the interesting presentation. I'd like to introduce our second speaker. It's with great pleasure to introduce Dr. Vern Sinroy. He is actually part of the ISU faculty and our ISU family. He first joined ISU in 1990, SSP 1990. He was I think he was the co-chair of the EO team project. And he has been involved with ISU ever since. He has co-chaired several satellite applications or space applications departments, as well as team projects. A side note is that when I was in SSP, which was about 11 year ago in SSP 03, he was actually my department chair at the time. So we're all very tightly knitted. He is currently the chief scientist of CSA's RADARSAT Constellation mission. His research interests involve the applications of advanced radar missions for disaster monitoring, resource exploration, and Earth and planetary studies. He was previously the editor-in-chief for the Canadian Journal of Remote Sensing, and he's conducted Earth observation projects in over 30 projects and international types of collaborations. He's also recently received the Canadian Remote Sensing Gold Medal and the Queen Elizabeth Diamond Jubilee Award for international contributions in global satellite applications. So please welcome Dr. Vern Sinroy.
Thank you so much. I think you've looked at my LinkedIn profile. Okay, I should change that actually. It's okay. I don't have notes, so I'll just speak to the slides. And I'm part of the ISU family, so you're all new faces. But as Suyin mentioned, that it is a family, and we're very close knit, and we help one another. So here it is. When I was asked to talk about the Arctic, I've gone to the Arctic many times to do work on exploration. I work for a department, and I'm glad I'm following our colleagues at the Canadian Space Agency. My department, go back, okay, my department is Natural Resource Canada. And as a scientist, my job is to help the government of Canada to find new resources and to manage it and to sustain it, make sure the environmental assets are being taken care of. Let's go back in the first slide. Here, he's helping me out. What our agency does, the Canada Centre for Remote Sensing, we are scientists. We're about 60 scientists. And we have folks that are developing imaging technology, image processing technologies of various satellites in the world for Canada. So my talk today, I just got 15 slides for 15 minutes, I gather, is to pick one or two of what my colleagues are doing to give you a message of what are the research areas that this particular Natural Resources Canada we're working on CCRS. And because I am the chief scientist for RCM, the RADARSAT Constellation, I want to hook our story of monitoring and mapping and the physics of understanding the environment in relationship to continued observation and the new physics and the rapid revisit of satellite with the Arctic. So the next one, if you can. There are 5 messages I want to leave. And each of the slide, one or two of these slides, speaks to these things. The Arctic sea ice is declining, and there's a few scientists in my agency. This is not my work. Some of it are mine. And I would show you how images are monitoring that declining, and what are some of the physics and the referee report that results from that. When you're looking at decline, the physical, have to look at age, the volume, the multi-year ice, and what's the implication? It affects shipping, and it creates hazards in the Northwest Passage. The glaciers are melting. There's a couple of slides show that examples and the physics behind it. The Arctic is getting greener. But as it gets greener, we found from a natural resource standard, the caribou are dying. Why is that the case? Well, through a few slides, I'll show that the permafrost are melting. What is the implication of the permafrost on infrastructure, on mining, on port development, and many other infrastructural work we're doing? I'll show some of the science involved from the imaging, from the geoimages standpoint. And of course, because this is my area of research, the permafrost and the resource side, when the ice is melting, the ground is open and we can see the rocks, and therefore we can find new mines. So on the resource side, I'll show you some example how we're moving on there. Okay, next slide. Here's an example. This is a quick, and this reminds me. This is MODIS. It's not a radar. Some of you have taken lectures from Scott Madry and Sulian and so forth, and knows that the radar is an active sensor. I will not stop being a professor, and the MODIS is more a reflective imaging. So this is a MODIS imaging, and it's subjected to cloud, but the point is to be made that if you look at 2004 over the Northwest Passage, which is a big deal for us, it's our northern highway, and then you look at 2007 and 2010, any grade 9 student would see that the sea ice is decreasing. This is a big deal. Why, when, how, and what are the understanding? So that's the fact, and there's many research that's been done, and others going to point you. Next point. The glaciers are also shrinking in a very big way. So here's a GIS product. Take all the red line. These are all the glaciers up in the archipelago, up in the high Arctic, and all the red areas at one point in time, time X and time Y, where it is. And through these papers in Canadian Geophysical Research have shown that the ice of the glaciers are melting, and this was taken from one of our colleagues at CCRS, and they're particularly tracking these over time, looking at volume, mass, the reasons, and many other reasons that goes to the physics of understanding the process. Next. The Arctic is getting greener. Well, the biologists have shown that if you look at the Arctic Circle, over time, it's getting greener for obvious reasons without going to the details. 1950, 2002, there's a visual data. But if you look at the science behind it, what's interesting in here is that the lichen, and this is a very important point, the lichen and the mosses are decreasing, but the shrubby vegetation is increasing. Now, this has huge implication of the wildlife, particularly caribou. And the scientists have shown that. Again, from CCRS, some of our folks have been publishing papers with regards to this ecotype. Next. Well, here's a good imagery from an Earth observation standpoint, a Landsat imagery, a topographic data that shows the variability of topography in slope on the valleys, a field photograph to show that this Arctic in these valleys in the high Arctic, it's greening, and a change detection image process imagery, time X, time Y, and you can put that and you can see from a policy standpoint the decrease and increase in vegetation. Notice the decreases are in areas of slopes. Well, what happens when it was covered by ice and the slopes are being exposed and you have moisture, you have landslides and so forth, and there's less vegetation. So that's a very convincing evidence, and it's in some papers that's been published by some of my colleagues at CCRS. The next one. Okay, here's a far more evidence which is based on field work. Now let's look at a caribou habitat. This widespread reduction of the lichen foliage. Now there's many reasons why the caribou are dying, but this is one of the many reasons, and an important one. If you look at 1965, 75 to 2015, at one time, there was 500,000, half a million caribou, and in 1985, in a particular area, this is not in the whole Arctic, and in 2015, there's 100,000 left. And these are based on population count. And when you look from a Landsat point of view, over time, on an image processing time-lapse imagery, and you look at the magnitude of the data, you see that greening over time. And here's an area in the Arctic where this has occurred. A lot of policy implications are involved here, given that a lot of our native population and so forth are relying on this. Next. Another point, permafrost. Let's move to permafrost. The ice, the ecosystem, now the permafrost. The permafrost is frozen ground. And when that ground starts to freeze, some of you are geotechnical folks, it creates problems. You cannot build pipelines, you cannot build highways, or you have an airstrip, things are very wobbly. And as a result, if you look at our Canadian Arctic, and it happens in the Russian Arctic, in Greenland and so forth, this is not, even in Antarctica in some places has been recorded. The point is that the Canadian government, we in Canada, and the American government in Alaska, we're planning a lot of major, it's like a 4-lane highway in the Arctic, pipelines that are going to bring down oil and gas and hydrocarbons to the US and various parts of Canada. And these are routes that are being planned. And they have to go through the frozen Arctic, the continuous permafrost, and discontinuous permafrost. Here's an example. This is what happens. This is a landslide. And it just creates in 2 years. This is the size of a soccer field. And consequently, you have tons of these. And within a 5-kilometer area along one of the pipeline route, there are 600 of these little landslides. That's the extent of where the implications of the Arctic. Next. Here's an image process. I think, I'm not sure if you've taught this in your class. It's a field they call radar interferometry, where we can look at the radar data and you can track over time and to measure the areas at risk for landslides as well as subsidence, as my colleague mentioned earlier. And along a pipeline route, if you're going to build a stable route, you need to search these areas where where the ground is not subjected to melt. And over time, we have tracked it, and this point shows between 2006 and 2010, the ground is shifted over a centimeter per year in various parts. So these are very important changes in the Arctic that affects our infrastructure and potential route planning. Next. Infrastructure, we have about 15 or 20 airports in the high north, and these are gravel runways. Some of you have traveled in the north know what I'm talking about. And well, when you have a gravel runway and now we have the paved runway, you're having these subsidence, and you can, there are safety problems. There are problems in, as our colleague mentioned earlier, in communities and so forth, and that's one implications for RADARSAT interferometry and for the RCM. When we have fast revisits of satellites, we can monitor these processes very, very early and know a lot about them. Next one. The coastal areas. Look, if you look at the high Arctic, along the Arctic Ocean, all the areas in red are major risk. Notice the erosion that's going on, both from an erosion standpoint, from an oceanographic and coastal erosion, as well as from a solifluction and landslides along these areas. So it's affecting, and so it affects these coastal areas, and for not only shipping, but port construction and all these kinds of things. We tend to watch it all the time and understand the process. Next. Okay. One of the things I work on a lot is to find new minerals and oil and gas in the Arctic and look at Earth observation. And there are two areas of interest here from a radar perspective and from a hyperspectral perspective. We can look at the mineralization of the surface. So what we do, we take things like topography, geology, geophysics, chemistry, and a number of other data, and we do a data mining in order to find these areas of new sites. So the imagery, basically, the message is by using these imagery, we're reducing the amount of time we spend in the field, and we are able to see these exposed rock, new showings of surface mineralization, which helps us in finding mines. And that's the message, is that as the frozen ground, as the snow clears up and so forth, we are able to see these things from space. Next. A little bit of physics. I can't stop by not doing the physics. So those of you looking at the Mars rover, where you land in on Mars and so forth, these are the fundamental questions we ask. When you look at the surface of Mars or the high Arctic, we can map the architecture of the surface. This is a sandstone, a very fine-grained material, a very coarse-grained material, and this is for landing sites and so forth. Based on the physical properties of the surface, we can characterize it from a radar imagery, hence RADARSAT, and look at the backscatter. The areas in bright here are the high backscatter, and we can map this geologically and therefore understand them and create these signature maps which are related to the high Arctic. Next. One of the big things, I think you mentioned, I'm in the planetary geology group at UNB, one of our universities here. We look at impact structures. And the Mars analog site in Devon Island, I work there quite a bit. What is the point here? Is from these images and the exploration standpoint, when you have an impact structure hit a particular rock, it pulverizes it. It makes it extremely pulverized, and the outer margin of the impact, where the limestone rocks are, so we can distinguish those rocks which are being affected by the impact and those which are not. And you can see the signature. These are radar signature, which are based on physical properties of the rock, in order for us to map in detail the Arctic. And why this is important, not only as a Mars analog. If you look at most of the mines in certain areas, there's a lot of mineralization on these edges. One of our biggest mine in Canada, $1 billion a year we pull out from that mine, is in Sudbury, and it's all related to an impact structure. So it's related to mining as well as Mars analog and so forth. So these Earth observation tools are very critical. Next one. Exploration for oil and gas, a big deal for in North. If you look at the Gulf of Mexico, one of the issue out of somewhere between the Australian Bight and Indonesia, some of the areas. But in radar imaging. My career actually was made from these kinds of satellites back in the 90s, and now we have, in 2018, we will launch the RADARSAT Constellation. This has 1 polymetric scatter, this has 4 polymetric scatter, and this one has 2 polymetric scatter, but a 5-day rapid revisit. So what we're saying is that as we understand the physics of backscatter, in the high Arctic, in these remote areas, we look at it with 1 polarization, in 4 polarization, and we can look at it every 4 or 5 days. Hence the physics and the monitoring is very, very critical, and this is why RCM is so important for Canada and most Arctic terrain. I'll end up with the last 2 slides, which is from science to policy. Next one. These are some policies, because you can do the science, the Arctic is greening, the ice are changing, the permafrost is melting, and we're finding new mines in oil and gas areas. What's the implication for the government of Canada from a resource standpoint? The Northerners are in the front line of this changing environment. Obviously, the risks are increasing. Arctic shipping is increasing. both from a temporal and a spatial standpoint. We need to understand that highway. We're looking at forecast and how we can do it accurately. There's a need for reliable information, and some of my colleagues would deal with that. The accuracy, the physics, the repeatability of the science as well as the policy, for regulation and for policy, and to support sovereignty, security, and resource development. And the last one is, we're not the only one, in the final slide. The World Economic Forum has a chapter on the Arctic, which I'm part of that conversation. And I think they sum up it very nice. A new publication, check this website out. It's coming out in about a month from now on the global agenda for Council for Space Security, of which the Arctic is critical. The words that they use here sum up what we're talking about here. Arctic climate change, rapid development, resource management, governance and conservation. The space-based solution is very critical for knowledge, refereed knowledge, and to avoid geospatial tensions, and particularly in the security area. And so I leave these are some big policy issues. These are some sample examples which you've seen that I've given you. So, and that's my story. Thank you. I have a video, but it's similar to what Guy shows, so let's leave that. It was a similar ice video, so don't bother with the video.
Okay, great, thank you, Vern. It's always a pleasure to have you here at ISU.
Thanks.
Our next speaker is actually a colleague of mine at the University of Waterloo. He is a professor. Ellsworth Ledru is a professor at the Department of Geography and Environmental Management at Waterloo. He received his PhD from the University of Colorado in 1976 and was appointed a university research chair in 2002 and a university professor in 2009. He also was awarded a gold medal by the Canadian Remote Sensing Society in 2005. He's a fellow of the IEEE and a fellow of the Canadian Aeronautics and Science Institute, that's CASI. His research interests include the climate cryosphere interactions using passive microwave, numerical climate models, remote sensing of coral biodiversity, as well as data management and archiving for the Polar Data Catalog. So please welcome Professor Ledru.
Thank you very much. My main area of research is in climate change in the Arctic, which is a very thought-provoking topic these days. And I've done a lot of field work in the high Arctic. What I'm not going to talk about, though, is that research. What I'm really going to talk about is data. And this can tend to be something somewhat boring, but I'm going to raise some questions about data that I think you as students and future scientists are going to have to deal with very shortly. First question, have you ever collected scientific data on your own? And the question is, where are they right now? I have to admit that 30, 40 years ago, I collected a great deal of data for my thesis. I could not find those data now. And when we're talking about environmental change, looking at data over long periods of time is very important. Have you used scientific data collected by others? And then the question is, how difficult was that to obtain? It's not such a simple thing to go to your neighbor and say, give me the data you've been working on for the last 5 years. I'd like to look at it to discover something. And then related to that, in terms of your own future, what will your contribution be? And I suspect that it will probably include some original data. Data either from the field, from satellite imagery, or from the laboratory. And that probably will be your legacy. That's what people will remember you for, some original data contributing to the scientific debate. So I want to talk about data and a revolution going on right now in terms of how we view data, manage data, archive data, but more importantly, how we convert it into information that people can actually use. Not just the scientists, but the native people in the north, for example, that want to know how the oil tracts are being sold off the Mackenzie Delta and what the impact is for their livelihood. There's a wealth of environmental data, but really what we're talking about in the International Space University is largely data from 1978 to the present. And just to give you an example, and this you've actually seen referenced before already, but this is sea ice for the Canadian high Arctic, the polar region. Typically, the minimum sea ice is found in September of each year. That's when the maximum melting occurs. This is the minimum sea ice for 1984. And it just turns out this is about the average for what it is since between 1978 and the present. So this is about the average of what we can expect. And you will notice that north of Alaska, the ice abuts the land. A lot of the Arctic archipelago is ice infested. There's ice going up the sound in this area, and a lot of ice between Svalbard and Greenland. This is the sea ice for September 2012. This is the minimum that we've ever recorded from satellite imagery. It's about half the size of that. No ice in the Bering Sea whatsoever. No ice in the Canadian archipelago. And Svalbard is not hooked up to the ice that's joining Greenland. These are major changes. And one of the major reasons is that the sea ice affects the global climate. It is this change in sea ice that some are arguing has caused the intense weather systems that we've had over the last couple of years, the intensification of the hurricanes and the triple whammy we had with Hurricane Sandy. It is also being linked to something called the Great Conveyor Belt, which will control the weather of Europe. This is not just an observation. This is something with global ramifications. And what about the future? This is what the forecast is from current information. This would be the sea ice in the summer in the year 2100. Right now, it's about here. So that little bit is what we're expecting. It will recover during the winter, but during the summer period, it will be almost non-existent. And I have got a very vocal former graduate student who lives in a Midwestern university, and he's saying we will actually see the ice disappear within 10 to 15 years. So that's just an estimate. What are the implications of that? Well, some people look to this as an advantage, and this is one. This is the route from Shanghai through the Panama Canal to Rotterdam. If we take that route right now, the trip from one way is about 28 days. What we've got here are the alternative routes if we have an open Arctic. This is the Northeast Passage from Shanghai to Rotterdam. The length is 18 days. That's 33% less. Not only that, the ships are larger. Each ship can carry 30% more cargo than the Panama Canal will restrict them to right now. So the whole issue of navigation, once the ice has disappeared, has opened up. What they have not considered is the fact that when the ice disappears, you have more icebergs. And they're a real hazard to navigation as well. So there's another side of the coin. So that's the type of thing we can get from data now. We're looking at current environmental change, we're looking at the processes of change, and we're understanding it more thoroughly than ever before. But as I said, that's really since the dawn of space imaging. In the past, we don't have so much data. I'm going to tell you a little bit about a program that we just finished called the International Polar Year, IPY. And the first International Polar Year was in 1882, 83. And this is a photograph from that period. This is taken on the north side of Greenland. I like to show this to my class and say this was a prototype graduate student at that time taking field observations. In reality, he belonged to the military. They sent the military out to do their observations. But the important point is, from that first International Polar Year that had 11 nations involved around the North Arctic, there's almost no data that is evident today. We've lost almost all of it. And whatever data we have is handwritten. IPY2 had 44 nations, 1932 to 33. Similar story. Very little of that data is available. Most of it was stored in Europe and was bombed out during the war. Think what we would be able to do if we had that data today and looked at sea ice and climate change in the Arctic going back to the middle of the 19th century. IPY3 was actually the International Geophysical Year, 57 to 58. We've got some data from then, but that was before computer recording. It was handwritten data. Recent IPY4, 2007, 2008, and the reason I mention this is this was a watershed for data management. In this particular case, we had over 60 nations, 200 different projects, and this is a famed honeycomb chart from there showing all these projects, and they involved a variety of things. First of all of these are for the Arctic, all of these are for the Antarctic, and these cover both polar regions. The vertical lines represent geophysics, land surface, people, oceans, ice, atmosphere, and space. And then there was also education and outreach. A lot of planning went into this. An important part of this is this bar here, integrated data and information services. From the very beginning, the International Council of Scientific Unions was one of the main sponsors. They said there had to be data management because they're investing a lot of money into this and we don't want to repeat past problems where we've lost information. Data management is critical. And indeed, one of the major outcomes of that program was an enduring data set, accessible to scientists and the public during IPY and for many decades into the future. That will represent one of IPY's strongest legacies. And with some pride, I point out that Canada was one of the few countries that took a strong interest in data management and actually put in millions of dollars into the process, whereas other countries had the scientists do this in their backyard computers. We actually had an organized program that took care of that, and that's what led to the revolution that we've got today that I'm trying to convince you is an important thing to build into your program. And why should we care about data management and archiving? First of all, preservation. If we can't preserve the data and go to it in 100 years, we can't synthesize scientific information. We can't look at new discoveries. It facilitates collaboration. We had got social scientists, natural scientists, medical scientists. They were all working together and sharing data and discovering new things that were not possible before in the context of individual scientists working in their individual silos. It encourages discovery. As we know now, the internet is facilitating things we never saw before. We can overlay maps brought from different sources, and we're finding out new things we never thought of. There's also an ethical responsibility. If we're collecting medical data, we have an ethical responsibility to manage those data properly and to preserve their anonymity and security. We don't want information about severe diseases getting out when the people are not supporting that. What we're finding now is it is a requirement for funding. The tri-councils are coming up with a data management policy, In NSF in the United States right now, you have to show that you've got a data management storage plan before they will give you money, and they will check that before they will give you another installment. And we've heard this before already. It meets the needs of the user community. And what I mean by the user is not just the scientific user, but the public. And one issue in the Arctic is that the greatest asset to the Arctic citizen is Facebook. They're separated, they're distances apart from each other, but they want to be part of a community. And despite the low download rates, Facebook is something they are all on all the time. And they're using that to access information to support their policy. They want to know what's going on. Yet, this is what we still are encountering. Scientists say, it's my data, you can't have it. I collected it. And I hear this even from government scientists whose taxpayers funded to collect the data. They still think since they physically went out in the field and got it, it is their data. And this is the reason I need it to publish. If I can't get that publication out and you use the data and scoop me, then I've lost my advantage. And in fact, in the journal Nature, 2009, there was a special issue on data management and data sharing. And you can't see what's written at the bottom, so I'm highlighting it here. Data sharing is good, but sharing your own data, that can get complicated. And in fact, what they suggested that data management should be woven into every course in science. And this is what I want you to think about. If you go back to graduate school, you might be finding data management as a requirement for your graduate degree. We're writing curricula now. We're realizing that this has to be part of the basic education, along with things like safety in the laboratory, field techniques, and things of that nature. The International Arctic Science Committee is a committee that oversees science development in the Arctic regions. And in April of last year, they came up with a statement of principles and practices for Arctic data management. And I think this is worth highlighting. When they endorse a scientific program, the results should be verifiable and reproducible through ethically open access to all data necessary to produce those results. That is, they're requiring a data management plan and some kind of an archive for every science program that's going to be developed in the Arctic. And those data shall be preserved and accessible and used in accordance with scientific norms of fair attribution and use. That is, you should cite who collected those data, just as you cite somebody's scientific publication. And indeed, we are getting publications now that are publishing data. So they become equivalent to referee journals in your CV and for things like merit and promotion. The real answers, though, are more difficult, but what we have found is that students want to share. This is the big revelation we found in IPY, where the students who were out in the field, they were not thinking of data as their profs were. They were thinking of data as they should share it amongst themselves. And in particular, I've been working with ArcticNet, which is headquartered in Laval. We do the data management for them. In fact, the students wrote the manual on how to manage data for ArcticNet scientific work. They were the people taking the initiative to do that. The second point is, citizens want to be involved with their tax dollars. This is government funding that's supporting this. The citizens want to know that they can access that data and get permission to use it. So those are two big drivers that are funneling this revolution in respect to data management that we're seeing. It was mentioned in the introduction that I've been developing the Polar Data Catalog, and I've been doing this for 20 years on top of my other research. This is one page of it, the Canadian Cryospheric Information Network. This is the data management for polar data. We've got ArcticNet, we have got data from the Canadian Space Agency, we have got data from Environment Canada, from WMO, from Aboriginal Affairs and Northern Development. What they're seeing is that this is a place that people can go to get information. And what you won't see here are numbers. This is information derived from data. We have got a Twitter feed. We've got a Facebook. This is a RADARSAT image that comes up at a different time each time you access this page. We've got a kids corner where we've got a game for public school kids to learn more about the Arctic and the science that's going on there. We've got news feeds, we've got FAQs and Ask the Expert, and we can actually get in and start searching data in the Arctic and the Antarctic and find that data and download it for our own use. And the big issue now is sharing data. These are the nodes internationally that our Polar Data Catalog shares data with. Yukon Research Station, the Norwegian Meteorological Institute, the Chinese National Antarctic and Arctic Data Center, U.S. National Snow and Ice Data Center. The last slide is going to show you why this is important, because management and preservation of data is really the key to the future. All of the science that we're talking about today and over the last few weeks is based upon data, and it's not data at one point, but it's data over time, and you have to be able to access that data, have confidence in it, and be able to use it in order to deal with future environmental problems. It is in the young scientists that we're seeing the transformation. It's a transformation in the approach to what we call stewardship of data and derived information. And the last point is interoperability. You've got to be able to share your data with nodes in other countries. There are international standards based on ISO. We use those, so if somebody goes into the Polar Data Catalog and does a search for an area of the Arctic, they can find data in that area that's stored in any other archive internationally. And we are now, the next stage is we're doing it for the Antarctic as well. However, there's still problems, so I'm going to leave you with this thought. This is something that was overheard in the lounge of the AGU fall meeting. Sorry I'm late. I ran into somebody whose data I want, so I had to be nice to him. So it's not smooth sailing. There's still a lot of challenges ahead, but I'm hoping that that will give you something to think about in terms of how you collect your data, use your data, and most importantly, acknowledge other people's data who have shared it with you. Thank you very much.
Hey, thank you, Ellsworth, for that fascinating presentation. Our last speaker is Dr. Lyle White. He is an associate professor at McGill University. He's also the Canada Research Chair in Environmental Microbiology. He is the chair of the CSA Astrobiology, DWG, and he's also served as a member of the CSA Space Exploration Advisory Committee. His research deals with looking at microbial biodiversity and ecology in the high Arctic. He studied the diversity, abundance, and critical roles of that microorganisms play in the polar regions. And lastly, he considers the Arctic as a Mars analog site for understanding and detecting microbial life in extreme environments. So please welcome Dr. White.
Thank you very much. It's a pleasure to be here, and I'd like to thank the organizers for the invitation and the chance to talk about my work. Is this thing working? Can you hear me well? Yeah, okay, good. Well, first of all, I'm a microbiologist, I'm a scientist, and I do a lot of work in polar environments, and I'm going to talk to you a little bit today about the relevance of looking at analog sites in polar environments, and particularly the high Arctic of Canada, and why that might be important in terms of planetary space science and research. So this is my colleagues that are indicated here. Let me figure out how this thing works. There we go. This is on Ellesmere Island, and this is a drill a drill that was developed or is in the process of being developed to drill into the subsurface of Mars to extract samples to look for little green bugs, if you will. And that's going to be sort of the essence of what this talk will be about. So let's go back a bit furthermore. Well, this is one slide I'd like to show to people just to give you an indication of what I'm about and my research program is about. And there's other people that do similar sort of things. I'm going to key on this part about here. I'm talking about astrobiology relevance, planetary space science, life on Mars, Europa, and Enceladus. And because this is a space science institute, I'm sure that we all know where those places are and why they're of interest. But to highlight that, when we talk about astrobiology, we're talking about looking for life on places in extraterrestrial systems. And our favorite places for looking at for life in our solar system are Mars, which you're well aware of. Some of you have probably heard of Europa, which is a moon of Jupiter, a very large moon that's covered by ice, and then we think that there is an ocean underneath that ice, a saline ocean. And there's another little moon called Enceladus that is a moon of Saturn. And this one's very interesting as well, and I'm going to show you a picture why quite soon. So, analog sites. Analog sites are places on Earth where we look at as potentially very similar to environments that exist on the three types of or three types of systems that I just showed you. This is some of these sites. There's more actually. The favorite analog sites, particularly when we're talking about Mars, are very cold and very dry places. And the best ones probably are on the Antarctica in terms of they're the coldest and let's say the driest. There's another one that's very popular as well and very useful. It's in the Atacama, which is the very high and the driest desert on the planet. The one in the Antarctica, the places like Beacon Valley and the Antarctic Dry Valleys are potentially better because they're also very, very cold. So you have the two extremes of being very dry and very cold. Way up here in the Canadian high Arctic, we have other sites that are relevant to looking for life on, let's say, early Mars when Mars was potentially warmer and wetter. So this slide shows, first of all, I'm just going to do you a very quick survey of some of the activities that are happening in the Canadian high Arctic and in some of these analog sites. The first one is on the Houghton Impact Crater, which Vern talked about a few minutes ago. Yeah, and this is a picture of the crater that's indicated here. It's about, I think it's 30 kilometers in diameter, and it impacted about 40 million years ago. Why is this important in terms of astrobiology? You're looking for life on Mars. Well, this is Gusoff Crater, a picture of Gusoff Crater, what it probably looked like about 3.54 billion years ago, where there was water on the surface of Mars, and we think many of these craters were filled with water. In fact, where Curiosity rover right now in Gale Crater, we're pretty sure there was a body of water that looked something like this on the bottom of Gale Crater. So this is the Houghton Impact Crater. I think was the hot spot of analog studies, and certainly in terms of Mars. And there was many activities that were occurring. This is in the middle of or on the side of the crater that's indicated here, and you can see some information on the bottom. There's something called the Mars Institute, the SETI, the Houghton Mars Project. The Mars Society operates something called the Flashline Mars Arctic Research Station. The Canadian Space Agency and NASA have also been heavily involved in using this particular impact crater to do analog operations such as remote operations, telecommunications. The CSA, for example, developed and remotely operated a greenhouse in this particular crater over a number of years. Other things that have been done here, drills for sending on robotic missions to Mars and other places, spacesuits, et cetera, et cetera. I think a lot of that activity has diminished in the last couple of years, but it certainly was in full force from about 2000 to about 2010. Now I'm going to take you to a place on Axel Heiberg Island, which is indicated, oh, wait a minute, we're going to go up to Ellesmere Island first of all. And there's another group of researchers that have been looking at a place on Ellesmere Island called a subglacial or sort of a superglacial spring, sulfur spring system as an analog to the Europa marine system under ice ocean system that exists there. And I don't have a picture of the ice on there, but this is what this system looks like on Ellesmere Island. You can see all the yellowing that's indicated here. And this is what we think is happening on the surface of Europa. And these individuals, this is led by Stephen Graspy at NRC Can. And I can tell you a little bit about the microbiology. There are microbial communities that exist in these systems on Ellesmere Island, and you can tell by the sulfur, the coloring there, that a lot of these organisms that we can find on the surface of this glacier on Ellesmere Island are essentially living off sulfur types of compounds, using them as energy sources, so on and so forth. So I'm going to finish off this presentation talking about some of the work that we're doing. And we're way down here in Montreal. And one of the features that I should mention of why the Canadian High Arctic has become a popular spot to do analog research, especially for Mars, is because it's relatively accessible. It's relatively easy to get to, especially compared to going to places like the Antarctica. So you can take a plane, a commercial plane, for example, from Montreal or Ottawa up to a place called Iqaluit on Baffin Island, and then take another commercial flight to this place here at Resolute Bay on Cornwallis Island. You can get there in a day. It's very expensive, but you can still get there in a day. If I want to go to the dry valleys of the Antarctica, I have to take a plane to New Zealand, spend about a week in New Zealand to wait for another plane that's going to take me down to the McMurdo station. So just to get there we're really talking about a week to 2 weeks just to get to from point A to point B, and the costs involved are greater. So you can get up here within a day, weather permitting. You can do the type of research that you need to do. You can come back within a week or 2 weeks or 4 weeks, depending on what you're doing. So this is very useful. I'm going to take you up to this place called Axel Heiberg Island, and some of the work that we're doing here in Expedition Fjord and Eureka on Ellesmere Island, to give you a sense of what we've been up to. This is Axel Heiberg Island here. Eureka is right there. The sulfur springs that I talked to you about on the glacier are up here. The North Pole is about right here, about 900 kilometers from this point here. And on Axel Heiberg Island in Expedition Fjord, we have the McGill High Arctic Research Station. This is what it looks like. Right about now, actually, I have 2 students that are up there. A very nice place to visit. So the first thing I'm going to say to you is show you something called a cold saline perennial spring. This one here is on Gypsum Hill. It's about this round. It's coming through 600 meters of permafrost. It is about 8-9% salt, about 3, 4, 5 degrees C, and there's a series of such springs that exist on Axel Heiberg Island like this. This is highly relevant in terms of looking for life on Mars because we think such springs may have existed there in the past and potentially still exist there in the present. From a microbiology point of view, this is sort of like a, how can I put this, a place where you can have some pretty interesting and amazing types of microbial ecosystems that occur. In fact, you can see the bubbles that are coming out of that spring. It's full of hydrogen sulfide, methane, CO2, things that microbes like to eat. This water is anaerobic, there's no oxygen in it, and we think that this spring flows, well, we know this spring flows 365 days a year in a place that has an average temperature of about minus 15 degrees C. So it contains a microbial ecosystem that does some pretty amazing things, and it does it in a system that could exist on Mars or has existed on Mars. I'm going to take you to another one, which is our favorite one. This is about 30, 40 kilometers south from the one I just showed you. It's called Lost Hammer Spring. And this little tufa structure here it looks kind of like a small volcano. Inside this is about 3-4 meters across, and the bottom of this little structure is a spring. And it contains about 25% salt. The temperature is about minus 5 degrees C, and there's a lot of methane coming off of this type of a spring. What you see around here, this picture was taken in July 2009, something like that, about 2009. This is all salt deposits because of the water that's coming out of there that's got this 25% salt. Okay? And it also contains like an active microbial ecosystem. And just to highlight why this might be important in terms of planetary science, looking for little green bugs on Mars. So we know, or we think, well, I'm going to say we think there's methane on Mars, okay? There's some controversy about this now. We had a report about 2008, 2009 that there was a detection of small concentrations of methane on Mars in the atmosphere of Mars, which for the astrobiology community is a sign of a smoking gun because there are microbes that exist on Earth called methanogens, or organisms that generate methane as part of their metabolism. And one of the sweet ironies of that is that many of you have methanogens in your tummies, okay? But they produce methane, And this is like a smoking gun signature, and we've long hypothesized that you could have such organisms living on Mars because they can essentially live off hydrogen gas and carbon dioxide, both of which could exist on Mars. Anyways, getting back to that Lost Hammer Spring, what we did show in terms of we have methane coming from the deep subsurface through 600 meters of permafrost. And that methane is a point source in a sense, but it also contains in the sediments of that spring microorganisms that love to eat that methane. And they can do that anaerobically without oxygen, and they breathe sulfate as part of that. Just like you and I breathe oxygen, they breathe sulfate. So that's quite interesting. So you can hypothesize that, we've all long suspected, for example, that methanogens could exist on Mars, producing some of the methane that we think has been detected in the Martian atmosphere, as an example. But there's other organisms that can eat this methane. They're called anaerobic methane oxidizers, or anaerobic methanotrophs. Trophic means to eat, methane, eating methane. Okay? So this is how these analog studies can potentially be used to better understand the types of life forms that could exist on some of these other planetary bodies as we move forward. This is just a couple of slides to show why this is relevant. On the sides of many craters on Mars, we find things that look like, the correct term for it is in a scientific basis are RSLs, reoccurring linear slopi that are indicated right here. The best hypothesis for such things that we see on Mars and present-day Mars that occur in Mars as we speak is that they are coming from liquid brines that are seeping out of the subsurface in that type of environment. So this is evidence of such a habitat could still exist on Mars. As we also go forward, here's a nice picture of Enceladus, and many of you have probably seen this picture or are aware of it. On the southern pole of Enceladus, there are geysers, if you will, shooting out saline water from the surface of Enceladus, which makes it one of many astrobiologists' favorite targets for looking for life. And we've had the Cassini mission fly through the plumes of some of that spray, if you will, that's coming out of the surface of Enceladus, and we know that it contains things like you see right here, methane, ammonium, carbon dioxide, other organic molecules that you see there. And as a microbiologist, a microbiologist, I can tell you that this is the kind of soup that we need to have a microbial ecosystem, because it's the things, you have a carbon source, you have a nitrogen source, you have something to eat, and you have something to breathe. And those are the four basic things you need to have in any type of microbial ecosystem. So the kind of things that we're doing again with the saline springs show you the kind of that such systems on Earth contain active microbial communities that can live on things like this is relevant to looking for the search for life on these other planetary systems. I'm going to finish off talking about permafrost, an extreme cryo environment. We had a couple of individuals already talk about permafrost, the problems that we're having permafrost. From a microbiological or astrobiology perspective, this is an extreme environment. It has sub-zero temperatures, background radiation for lengthy time scales and the geological time scales, very low water activity, which means that although it's full of ice or it can be full of ice, none of that water is actually available for life to use. It's frozen. And it has extremely low rates of nutrient and metabolite transfer, so things can't get in and get out. So this is an extreme environment. I can show you slides of the type of microbiology ecosystems that live there, and we know that through the kind of research that myself and other people have been doing, that such permafrost doesn't contain, or most of it does contain, active microbial ecosystems working at very slow rates, but nevertheless exist there and are viable. Why is this important from a astrobiology point of view or an analog point of view? Well, this is a picture of, I'm going to show you this one. This is the Phoenix landing site taken in 2008. This is a typical polygon type of geomorphology that you would find around the Phoenix landing site. You see these troughs that are indicated here. This is sort of what you see in a polygon area. This area here is right adjacent to the McGill Arctic Research Station. In fact, these barrels that you see here are lining up, and this is the runway of the McGill High Arctic Research Station. And I don't know if it was Vern that mentioned that, about how the Yellowknife runway is having problems. Well, we have a major problem right now because of global warming, and the global warming is most extreme in the high Arctic regions of the world. These troughs that you see here are essentially thawing because underneath them there's an ice wedge. and the ridges are getting bigger and bigger, and we're starting to have a major runway problem. In fact, we don't know if we're going to be able to access the McGill site using this landing strip in the near future, unless we can figure some way out of doing it. So it's not Yellowknife, but it's the same problem. So yeah, here is Phoenix, and this is one of the first images that came from Phoenix after it landed on Mars in 2008. And people like myself who work in Arctic polar regions, when we saw this picture, we all jumped up and said yes, because we could see the polygons in there. And what Phoenix did also found was that there was ice in the subsurface. So there is water on Mars. There's lots of water. It's all frozen. And what we know about life on Earth, microbial life on Earth, is that we know from the Arctic regions and the Antarctic regions that you can have microbial communities that could exist in such an environment. So that was what makes it a useful analog site. I have about 2 or 3 slides left. Let's see. Yeah, well, this is one of them. Okay. This little guy here, this is a microorganism. It comes from Ellesmere Island permafrost at Eureka. It's part of a NASA ASTEP project where we were the microbiologists that were brought on board in the hopes of developing a robotic drill to eventually send to Mars. And this was done with NASA Ames people. So this organism grows at minus 15 degrees C and about 18% salt, and it can breathe or respire or do things essentially like you and I are doing right now, at least down to minus 25 degrees C, which makes it the cold temperature champion of the planet. We know of no other microorganism that can grow at lower temperatures in such extreme conditions. And we are studying this extensively as we move forward. And I'll just end off finishing here, talking about, again, getting back to the theme that has been reoccurring this evening, this idea of global warming and the changes in the Arctic. And you can see the very dark red areas up here in the high regions of the higher latitudes of the Arctic, and these are the regions that are essentially warming up faster than any place else on the planet. We can feel this even in the short trips that we go up there. I've been going to the Arctic since, I think, 2000. Just to give you an idea of these changes that are occurring, for example, around 2010, one of my graduate students said to me as she was going up in July 2000, said, "Do I need to bring any bug spray?" And Professor White said, "Of course you don't need to bring any bug spray. There's no bugs up there. There's no mosquitoes. It's too cold. We hardly ever see them." Of course, it was 20 degrees that year, and there were swarms of mosquitoes. So now, you can just see these small changes that are occurring. And you can see the latitudes there where the greatest temperature anomalies have been occurring that are indicated there. We talked about permafrost melting and permafrost warming. Again, some of other speakers alluded to this. The problems that we're going to have in terms of land shifting, melting, so on and so forth. Well, we have another problem here too. And you can see these two things called CO2 and methane, which are greenhouse gases. The Arctic regions, the permafrost regions of the poles, contain huge amounts, especially the Arctic, of organic carbon that is frozen or has been frozen in the permafrost layers, the upper permafrost layers of the planet. And the projection is that in the next 80, 90 years that we're going to lose about 3 meters of the surface of or permafrost is going to melt. And the problem is that as this permafrost melts, the microbial communities that exist within them that have been either dormant or being essentially metabolizing at extremely low rates are now going to take this organic carbon and through its microbial metabolism transform it into methane and carbon dioxide. And we think, for example, that this potentially could add another 50 parts per million of CO2 to our atmosphere in the next 50 to 100 years. So I think we talked a lot about Earth observation systems earlier on today, and there was a satellite that was launched about 2 weeks ago called OCO2, which is going to be measuring CO2 concentrations as an Earth observation system on a planetary scale, and I think as well as the Arctic regions. We need another Earth observation satellite that's going to measure methane and see if these predictions actually come true, because they will have effects as we move forward. Thank you very much.
Thank you, Lyle, for that fascinating presentation. At this time, I think we'd like to ask our panelists to come up to the front on the stage. We're going to set up some seats here. And I wanted to add on that when David Kendall and myself were putting together this panel, we purposely chose a range of speakers related to space in the Arctic. So I think we've managed to touch on a range of topics from space applications to even policy and law, data management, to life sciences and astrobiology. So now the floor is open to questions. I think we have a good half hour, and I think we have some mic runners as well. So we'll open up the floor to you. Okay, Zach?
One of the presentations showed that the melting ice and the permafrost is revealing new resources in terms of mining and oil deposits. And it seems to me that our current Canadian government will have no problem handing out leases to those areas that will, of course, exacerbate the problem. Can you speak to that, or what you think we could do to mitigate that?
Vern wants to say some words.
I'm sorry, can you repeat the question? Where are you? Put your hands
I'm
up.
over here.
Okay, the young man with the red shirt. Okay, talk to me.
So that the ice is melting in the north and revealing resources in terms of minerals and oil deposits. As commercial and industrial developments move into those areas, it will cause more a positive feedback loop in that area. Should we mitigate that? Should we increase commerce in that area? What can you see happening in the next 20 years?
Should we mitigate that? The answer, yes to all of the above. One of the things, the science I talked to you about is that, let's take oil as an example. You find an oil in the north, you have to distribute that oil through pipelines or whatever you. And to build a safe pipeline with a shift in foundation, you have to monitor that shifts. Hence, things like Earth observation in the sense of the RADARSAT Constellation, which we are watching that area every 20 days. Now we're required to watch it every 2 or 3 days, hence constellation. Because we cannot put the sensors over a 2,000 kilometer over a shift in terrain. So there's many things at stake here. As you mine these resources and you bring out the raw material, whether it's oil, zinc, copper, gold, you have to truck it out or pipe it out or whatever you. An infrastructure in the high Arctic or the mid-Arctic is the same as in the city. The geotechnical engineering and the monitoring of building robust systems is enormous. So yes, we need to mitigate it. We need to integrate the sensor in the ground to look at melt, to integrate that point data with a spaceborne data and create an integrated monitoring tool for these shifting terrains. So once the high Arctic, we have a lot of resources. Folks like us are mapping those resources, but we have a huge policy issue in bringing out those resources. We're not there yet, but there's an integration of science. So your question, do we need to mitigate this? The short answer is yes, robustly, and every day of the year, so to speak. Space assets is one of them. Does that answer your?
Okay, next question. I think we have one over there and maybe number 2. If we, there's 1, 2, and 3. And also, when you ask your question, we'd like to request you to state your name and maybe where you're from, too. Thanks.
Hi, I'm William from France. One of the presentation was about the importance of sharing data to create value and to create a user community. And in the other end, we have presentation about RADARSAT and the tremendous benefits, societal and environmental benefits of RADARSAT. But in fact, it's all the data are really restricted because it's really expensive to have access to this data. So finally, it's preventing the development of user community. So is there some lessons learned to influence the new data policy of Constellation, or it will be like restricted or open?
Okay, first of all, the RADARSAT 1 data for the polar regions is available on the Polar Data Catalog. And the reason it was put there was because it's outside the government, and they were able to change the policy. So those data are available free of charge to anybody internationally. So no longer do you have to pay for it, and no longer do you have to have a valid scientific program to access those data. We're also putting up the Antarctic mosaic data for RADARSAT 1 and RADARSAT 2. And we're trying to get RADARSAT 2 data up under the same policy as well, but the issue is that it belongs to a private corporation. So the government is now trying to work with them through a licensing agreement so that we will be able to do that. So it is moving towards open access, and a lot of other government data is moving in the same direction. And part of the reason for that is the movement of the scientific community. So it's a question of push by the scientific community that's making the agencies respond to that. And I'm going to pass it over to Vern for the Constellation in a moment, but there's another major player, which is GEO, the Group on Earth Observations from Geneva. And they're a consortium of over 80 different countries, and they are dedicated to free and open access of spatial data globally. They're having some issues, but they're moving ahead so that anybody can get access to data. So you might want to look at that as another source of data, but also another push towards changing the policy.
On the RADARSAT Constellation, Ellsworth mentioned the operative word. We are moving, at least the Canadian Space Agency, the government of Canada, they're moving towards open data policy. RADARSAT 1 is private-public, RADARSAT 2 private-public, whereas Constellation is strictly owned by the government of Canada. And we have designated what we call priority sites already. Areas of earthquakes, areas of landslides, strategic infrastructure, the Arctic. These are sites where there's going to be open data. The policy is currently being written and it's near to finish, so we are moving towards that data sharing. Robust data sharing and standardized data sharing.
Are we going to go with Elias at the back, or I think there was a question over here. Yeah, okay. Starting out the order here, okay.
Hi, my name is Elias from Brazil. You like data and I like history. You said that in the 50s there was some data already collected, but they were handwritten. And I'm wondering, do you have any knowledge about what they knew about it? What do you know that they knew already was changing? What can we know from the past that can explain now the future, if you know something?
Are you referring to the data from the 1957, the International Geophysical Year? And there are a lot of science came out of that, and the data are available for doing that. And actually during this IPY, they went back to that data. It's actually a generation ago, so some of the scientists that were collecting as graduate students in 57 are now the chief scientists in this IPY and using their own graduate students. So it's not so long ago that there's not that continuity. To say exactly what we're getting out of it is beyond what I can answer to right now. But for example, in Canada, one of the big issues is lake ice and sea ice. And I showed you some of the maps of sea ice going back to 1978. We have got maps of sea ice in paper form that are going back to the 1950s from the Canadian Ice Service. And they're actually now trying to reconstruct that into a digital form so that we can start extending that record going back as a coherent data set. And this is an area called data rescue. And a lot of that is happening now. We're realizing that as profs are retiring, they've got these masses of papers, as you might expect, sitting in their office with data in them. And they're now trying to get people that will transcribe that data, make a digital record of it, and put it into the archives. Things like photographic data, for example, for looking at glaciers. So you've got photographic history of glaciers at various times in the past that can be used for scientific analysis. So I'm not answering your question directly because I can't say what a specific study is, but this whole idea of data rescue is now recognizing that we need those longitudinal data sets, and we're going back and trying to recover them as finances are available. Having said that, that's probably the lowest priority data activity around, unfortunately.
Hi, my name is Masanori Muto from Japan. I almost had the same question as William. I'd like to ask about the open access data policy. My question is there any difference between the open data policy of raw data, processed data, or value-added products like that in the Arctic Science Committee?
I'm sorry, are you asking whether there's a different data policies for the level of processing of data?
Yeah.
And are you referring to satellite image data?
Especially satellite image data, but it's not limited to satellite data. I'd like to know the different arguments on the level of the data policy and the level of accessibility to the data and the products.
I don't know if I can really answer that. Maybe somebody else can look at that. I know that where we're sharing data, it is at the most basic form of information in terms of satellite data, the basic process data, as opposed to looking at derived data, which might be, for example, vegetation index data, which are usually scientific things. So we're looking at the basic level, and we are working with Japan right now to share those data. And typically, those are the data that are mostly clearly documented and in using the international standards so that we can share them. When you get into derived data that people built for a paper, typically there's a lot more processing and the standards aren't being adhered to.
Yeah, just to add to that, the current data, let's say take RADARSAT, there's various level of processing. In some of the labs, you need a raw data to look at the radiometric and fidelity of the data. Yeah. But for the public, you may need level 1, level 2, level 3. So level 1 it is just generally corrected, so you can put one pixel on top of the other and so forth. Level 2 is a thematic data that you can do some more correction. So the policy, if it's, for example, in the Arctic, you would have data, they have NDVI and various other thematic data. So you can only give general information. There's very specific policy attached. Okay? Definitely raw data is fine and level 1 is fine. But the others, I think it's debated.
Hello, my name is Susan Jewell. I'm representing United Kingdom, and my question is more of a microbiology and astrobiology question. I'm interested to know is McGill and or your organization working on the waterbeds, the tardigrades, quote unquote, the mini astronauts, And what is your thought on using them potentially one day to terraform maybe Mars?
Well, I'm not. They're too big for me. There are other people that have been looking at, for example, on Ellesmere Island, we know on the ice shelves that there are such creatures as tardigrades that exist in the ice shelf microbial ecosystems on the northern tip of Ellesmere Island. I haven't heard of them being used, for example, to terraform Mars. They are eukaryotic cells. As far as I know, they are aerobic cells, so they need oxygen to survive and grow. So I don't know if they'd be the best candidate for that sort of thing.
Hello. Sir, you have talked about many climatic changes happening. So what is your opinion about that? How much risk are we at present about the future of the environment and mankind as a whole, considering the present climatic changes what you are observing? Like, are we at a real risk, or like do you envisage something really alarming which may come 50 years down the line, considering the changes which you detect?
I just had a dinner with some friends on Monday night, and the topic of climate change comes up because that is my major field. And I feel like every time I mention that, I completely ruin the dinner evening because nobody wants to hear this very sad story that I've got to tell. First of all, there is no question that the climate is changing. And there's no question that we have caused this type of climate change since the start of the Industrial Revolution. People will argue that there have been higher CO2 concentrations in the past, and indeed there have been a very long time ago, but they have not been human-induced, and that's the distinction. We are causing the change, and if it's going to be controlled, we have to mitigate and adjust. The difficulty is that current research is suggesting that even if we did something today that was dramatic and incisive, it would not have an impact on the climate until the year 2100. The point is there are reservoirs and what we call thermal flywheels in the system. One of the biggest ones is the ocean that softens the signal so that no matter what we do right now, it'll take a long time to have any impact. However, if we don't do it now, it's not going to happen in 2100 years, at 2100 years, and it's not going to happen after that. So we do have to do something, but it's for another generation. And really the change that's going to be required is not geoengineering, but it's going to be a change, in my opinion, in the culture of how our children manage their lives on the planet. And for example, a few things we didn't realize until a few years ago, the amount of CO2 that's created by all the aircraft over the world is equal to the amount of CO2 created by all the computing facilities we've got. Those two are the same value. We just came up this week with a study about all the CO2 that's resulting from all your personal devices being plugged in to be charged each night. It's not a trivial amount. Those are things which are contributing to the problem that are part of our lifestyle. And we're making decisions to adopt that. And so a lot of it is political, and a lot of it is social and cultural. And it is a question of modifying our response to our needs. That's going to be the biggest change in the future. The physics is unequivocal. Something's happening, it's going to be a long-term solution, and there are things that we can do, but it's up to the individuals to do it. And whether we're successful, we won't know. Is that for a bummer?
My name is Rory. I'm from Canada. I'm interested to hear that geoengineering was just mentioned. I was wondering whether you could comment on the, I guess, perhaps the viability and the ethics and whether or not that's a good idea.
I'll start. I know nothing about this, but I think it's a really dumb idea. Trying to make large-scale changes to our environment by geoengineering, the consequences, the unknown consequences of that will probably be, worse than what we think the good that it's going to do for it. What we really have to do is get off our hydrocarbon addiction problem. And when we do that, then we're going to really start resolving our greenhouse gas problem.
Let me give you an example related to that. As you probably realize, to get rid of the sea ice in the Arctic would only take covering it with a very thin black layer. And so just covering the sea ice in the Arctic with soot would absorb a lot of solar radiation and melt it, and then the ice is replaced by the water. And then you've got the situation that I forecast 80 years from now. Back in the 1950s, the then Soviet Union had a very active plan to use their bombers to spread carbon soot over the entire Arctic sea ice. The reason they wanted to do that was they had to grow more grain further north into Russia to feed their people, and they had to have a warmer climate to do that. And so their thought process was, if they open up the Arctic basin and have basically the Crimean climate on the shore of the Arctic basin to Russia, they would then have the Ukraine steppes, which is where all their grain is being grown now, in the north side of Moscow. And therefore they would have all the food they would require for their people, which were having droughts at that time. Now, we know that that would not have been a solution, but that was a geoengineering solution to their problem as they saw it. And that's the issue. Whenever you've got a solution like that, you've got a certain constraint in terms of how you frame the problem, and you probably don't know of all the impacts that would have. And if Russia wanted to do it, they didn't care what the impact would have been on climate change in the Mediterranean. And there would have been a climate change in the Mediterranean. But we wouldn't have known it back then. And the United States and Canada were not in a position to be part of that discussion. So you've got an engineering issue, you've got a science ethics issue, and you've got a geopolitical collaboration issue in all of that. And those are the problems with geoengineering solutions. Some of the problems.
Hello, my name is Sun Jun from China. My question is, once the Arctic channel opening will greatly influence the world's energy and trade pattern, at the same time will affect the local ecological environment and the residents' life. What's the policy of the government? Thank you.
I want to say I don't know, but that's, I'm sure. I'm a scientist and I don't deal. Are you? Let's be specific. Are you asking the question of the Northerners? Well, the policies currently, and I know for Natural Resource Canada, as a scientist, the policy is currently being developed. We are acquiring a lot of data. For example, permafrost. Schools are shifting, highways are shifting, runways are shifting. So we're collecting more data, we're doing a lot of mitigation. The risk is getting higher and higher, and therefore we have to mitigate it. So obviously the policy is to look after the folks, given the physical properties of what's going on in permafrost melt in this case, in temperature changes. So the government looks after its citizens with the best scientific data they know how. Now there's a lot of policies on, there's many mechanisms. There's Arctic Institute, there's collaboration, There's many discussions going on, even I'm sure my last slide, the World Economic Forum. So it's a layered policy. So if your question is, what is the policy of the government of Canada, you will find a policy book with 10 chapters referring to caribou, Inuits, pipeline, runways, port building, trafficability. So you see, so there's those kinds of very specific and there's a larger issues. Okay? I don't know if I answered the question.
Joe Pelton, faculty, and I'd just like to come back to the reports about the 50 parts per million that could come when the peat fields in Siberia melt and release huge amounts of gas. Basically, through history, I think we've had 5 mass extinctions, one from the K2 asteroid and the others, though, from basically climate change and heating. It seems to me that we really do need to spend more time to convince political leaders the variety of things that have to be done. In other words, weaning ourselves off of hydrocarbon fuels, but also the other activities that perhaps we can do to not only move to solar energy, but one of the things that I'm currently working with Dr. Ram Jaku at McGill University is the reports for the World Economic Forum, and the next stage will be sort of the vulnerabilities that we have as a planet and how space can help save our planet, so to speak. And I just wonder if we could have comments about to what extent do we have a responsibility to convince political leaders that there are solutions, but there are things that have to be done and done sooner rather than later, because what we do now, as you indicated, would be 2100. If we wait another 50 years, maybe it will be too late altogether.
Yeah, well, I'm the academic here, so my friends in government here probably don't want to answer that question. Well, the Canadian government, I'll tell you, the American government, your government seems to be, right now anyways, much more open to the idea that we have a real problem. The Canadian government, on the other hand, you know, and I'm speaking in a very general sense here, doesn't seem to really want to buy into that line because of certain of their own policies and the tar sands and all these sort of things that they think is very important to the Canadian future. So how do you convince, for example, the Canadian government that we're doing a lot of harm by developing tar sands when those tar sands are paying for our universities and our hospitals and everything else? That's a tough thing to do, very tough thing to do. And one of our other speakers mentioned to the fact, how do you convince this generation that we have to do something now to help our generation, the next generation, or the generations that are going to occur in 2100. It's very hard to convince, for example, my brother-in-law that he needs to buy a smaller car and be more fuel efficient. Who's not a scientist, he doesn't care. In many Canadians, as an example, global warming for us means longer summers, and we view that as a positive thing. So that's the Canadian context. That'll be the starting point here.
Well, actually, there is an anecdote of a very noted Canadian meteorologist who was a senior government bureaucrat at one time, and he went to a parliamentary committee on climate change, and he was very highly respected by the government. And people were asking him, why should they care about climate change when their mandate was measured in terms of 5 years? It was that crass about the time frame that they were thinking of. And his response was, you have to think of it in terms of your grandchildren, not your own life. And that didn't really have a very strong effect. And yet we have a prime minister who's quite interested in the Arctic. And they're putting a lot of money into the Canadian High Arctic Research Station in Cambridge Bay to support Arctic science. But a lot of us are wondering what kind of Arctic science. Because just up the stream, they're selling off the oil tracts off the Mackenzie Delta for drilling rights right now. So it's very difficult for us, and I'm an academic as well, so I'm not part of the government machinations, but it's very difficult for us to understand what are the pressure points to make things happen.
We forget that there's more than people on this planet.
Mm-hmm.
All the large mammals are endangered species at this point.
Well, you mentioned the 5 extinctions. You should read a book that just came out called The 6th Extinction, which is us.
Right.
It's called The Anthropocene.
Okay, so on that positive note, I see it's 10 o'clock, and I think if you have any remaining questions, there is a reception. I think it's going to be on the side hall. But before we go off to the reception, I just want to sincerely thank our panelists for contributing to this event today. Vern, Ellsworth, Lyle, and Guy, we really appreciate your contribution to this panel event. And for everyone else, for the participants and audience, I hope you all have a good evening and also a great early start to workshops and TVs tomorrow. So we'll head off to the reception, but a round of applause for our panelists.
Thank you.